welcome everyone. And today we are happy to have Ricardo Monteiro, and he will speak about double copy. Please start.
Okay, well, thank you very much for the invitation. I will give an overview of an area in which I've been working on for some years now, where people try to express gravity as a double copy of gauge theory, and I'll tell you what this means. So I will give a broad overview, and I will not go into enormous detail into which of the particular topics. I will go into more detail into some of them, of course. Well, I will start by giving a brief introduction of this and its origins in the study of scattering amplitudes. And then I will discuss how the same ideas can be applied to certain classes of classical solutions, so solutions that we actually know exactly. And finally, I will go back to the scattering amplitude story and connect it to more directly. Okay, so let's start with a brief introduction, and I hope that this will be accessible. Also, I was told maybe master students could show up, so I hope this will be accessible to almost everyone. Right, so scattering amplitudes, they tell us about the probability amplitude of going from some in-state. Can you see my cursor here moving?
Yeah.
Okay, going from some in-state where we have some particles to some out-state where we have some other particles. And this can be calculated using Feynman diagrams, as you know. And Feynman diagrams, well, they are great in many ways. They're the basis of much of our knowledge of particle physics. They apply generally in perturbation theory. They give a very clear physical picture of the ways in which the interactions can occur. But they also have big disadvantages. So it depends on the problem that you are looking at. When you have many external particles, when you are very high in the perturbative order, so in the loop order, then they can be quite inefficient. And connected to this, they break some symmetries that you may want to keep. Well, a basic example is gauge symmetry. So individual Feynman diagrams are not gauge invariant, only the sum over diagrams is gauge invariant. And there are more sophisticated symmetries that people consider. And Feynman himself, let me just give you this quote, he encourages to look at things in different ways. Every theoretical physicist who is any good knows 6 or 7 different theoretical representations for exactly the same physics. And this has been, I guess, given the relative lack of experimental data, this has been certainly a big drive for modern theoretical physics. Now, in scattering amplitudes, there are many modern approaches, and one of the themes is to explore the relations between the S matrices in different theories. And here I'll be talking about gravity and gauge theory. And these are relations which are typically hidden in the usual approach of Lagrangian, Feynman rules, equations of motion, etc. Now, gravity is really somehow the perfect arena to look for new things that may help us, because perturbative gravity is pretty hard in the usual approach. So in the 60s, people try to apply, typical, well, the basics of field theory to the Einstein-Hilbert Lagrangian. You take your metric, you expand in a graviton field around the Minkowski backgrounds, and then you get a mess. Well, this is the 3-point vertex. This is from DeWitt's paper, now more than half a century ago. So there's some symmetrization of indices. This P6 means there are 6 terms, which are permutations of indices. Also here, this is the 4-point part. This is a P24, so 24 terms just here. Okay, this is much worse than usual in Engel's theory, and there is an infinite number of higher point vertices. Although, of course, at each order in perturbation theory, you only need a finite number of them. And people have used it. It depends what problem you are looking at. But clearly, yeah, you would like something a bit nicer in general. And this was a big motivation to develop this technique of looking at gravity as a double copy of gauge theory in scattering amplitudes. So let me start by discussing first the asymptotic states in the scattering, so the in or out states. Now in Engel's theory, these will be some gluons. So these are just linearized solutions to the equations of motion. There's some plane wave with a momentum K, which is null, some Lie algebra elements, and some polarization. And in d dimensions, a massless vector has d minus 2 degrees of freedom. So that's the number of independent polarizations you have. So in 4 dimensions, it would be, for instance, positive and negative helicity, if that's the basis that you want. Now, for gravity, you can consider a polarization tensor. And now, let's suppose that we take 2 polarization vectors and we get a tensor. What theory do we get if we consider these objects, or actually any linear combination of such monomials of this factorizable type? Well, you get a theory that has not just the graviton, but also fields called the Dilaton and the B-field. So you can think about the polarization tensor for the B-field as the anti-symmetric part of a combination like this, the Dilaton, the trace part, and the graviton, the symmetric traceless part. And this theory has, as you can think of, if you think about the basis of polarizations and all the things you can have here, has d minus 2 square degrees of freedom. And this is a generic property of the double copy. Here I chose pure Yang-Mills theory, just gluons, but you can choose supersymmetric extensions, for instance, and the number of states in the gravity theory will always be the direct product of the states of the gauge theories that you choose. You can choose 2 different ones, let's say supersymmetric and non-supersymmetric, for instance. Now, so these are very simple things, just at level of the free theories. But what is more surprising is that if you consider states that are factorizable like this, and then you can obtain other ones by linear combinations, then this factorization is preserved by the interactions. If you look at, if you represent your interactions in an appropriate way. So you get formulas, of which I only present here a schematic form, where a scattering amplitude for gravity states of this type, which are factorizable, really does factorize into some kind of product of scattering amplitudes for gauge theory for these left polarizations here and these right polarizations. Now, of course, you have to strip off the color. There's no color in gravity. And then there is also, you have bidimensional analysis, and also to fix the propagator structure, there are some inverse propagator factors. So the particular realization there are different realizations of this formula. I will not describe it in detail. What I will show you is that there are some completely analogous formulas which apply to classical solutions. Now, a famous application of this kind of story for sketching amplitudes has been the study of the ultraviolet behavior of supergravity theories. So let me just tell you that at loop level, this kind of relation works at the level of the loop integrand. So the idea is that you construct the loop integrand for your favorite supergravity. Well, depending on, you have to choose what are the appropriate gauge theories that go into the double copy. And then you check what is the critical dimension after which you have a UV divergence. And what has been checked is that, unlike what was thought, let's say in the 80s, maximal supergravity at least is finite up to 5 loops. I would say most people believe it will not be finite starting at 7 loops, but this is something that, this is a kind of problem that can only be, checked having something like this. So this is what allowed for the progress that did not occur since the 80s. Starting at 3 loops, and then 4 loops, and more recently 5 loops. Okay. Now, this story of the double copy, its origin, although you don't need to think about string theory to think about the double copy, but that's how it was first noticed, because string theory brings a very different perspective on field theory. If you think about field theory as the limit of string theory when the parameter alpha prime goes to 0. So this parameter is the string length. Hence, when you look at string theory at low energies, that's large distances. So if the string length, if you can neglect it, then effectively it behaves like a particle theory, like a field theory. So if you think about particle sketching in the usual way, you sum over many Feynman diagrams, but in string theory, you have a single diagram at each order in perturbation theory. So here I'm representing the scattering of closed strings. So they are these little circles, and there's a worldsheet interpolating between them. in this worldsheet, a two-dimensional CFT lives, and that CFT dictates all the interactions. Because it is a CFT, you can turn this into a correlation function on the sphere, and the external states are represented by some so-called vertex operators. So this is good to have a global picture of the amplitudes. And just complex analysis on the sphere actually takes you a long way to understand some algebraic properties of the amplitudes. In particular, the relation between the scattering of closed strings and open strings, which at low energies then has a direct implication for the relation between gravity and gauge theory. Now, this double copy relation appears at the level of the asymptotic states in a very similar way that I mentioned before. So for the closed strings representing this kind of zero mass gravity states, they just sort of factorize into ones that that look like the vertex operators for open strings with the left polarizations and the right polarizations. And in the 80s, Kawai, Level, and Tai, in a beautiful paper, they showed how to, what was the implication of these at the level of the scattering amplitudes. So to calculate the closed string amplitude, it's not just a correlation function. You have to integrate over the moduli space, which means that you have to integrate over the locations of these vertex operators on the sphere. It's a two-dimensional integral. And what they did was to disentangle that into two one-dimensional integrals, which can be interpreted as integrating vertex operators on the boundary of a disk up to some phases. And well, I here in a bit misleadingly, I represented the disk as being, like this, so that you can think about gluing it into here, which is not really a very, it's not really how you should think about it, but okay, it just gives a visual picture. You get the amplitude for closed strings somehow as a double copy of the amplitude for open strings. And you take the field theory limits, and you get then the field theory case. And there are different formulas for these, the KLT, so this is based on the string theory one, BCJ, which is a diagrammatic approach, that's Bern, Carrasco, Johansson. There's the Cachazo-Hey-Yu one, which is a string-inspired way, which is valid only for field theory. Okay. Right, so why is it simpler? And I'm just going to give a pedestrian example now. So let's think about three-point interactions in gauge theory and how they double copy to gravity. You can look up the three-point vertex in Engel's theory in a textbook. So this is the structure constants of the Color-Lie algebra, and this is the kinematic part of the vertex. Then you can define a gravity field, so sometimes called the fat graviton. Actually, Alex and I were together on this, which combines the graviton, the dilaton, and the B-fields. And then the three-point vertex for an appropriately defined fat graviton is that this is the double copy of the kinematic part of the Engel's theory vertex. And what is interesting here is that here you have two indices, left and right. And here, these indices don't talk to each other. So the unprimed and the primed ones don't talk to each other. This is very much unlike what you would get from the Einstein-Hilbert Lagrangian. So this reduces the tensorial structures that you would naively expect to get and that you do get generically in different approaches. So this index factorization is just a basic view of why things will be simpler than these horrendous Feynman rules that I mentioned before. And the powerful implementation of this beyond 3 points is the so-called color kinematics duality, which I will not have time to discuss here, which has played a big role in the story for scattering amplitudes. Now, there has been a lot of interest more recently in applying these to classical perturbative gravity because of, well, gravitational waves and the new era of gravitational phenomenology. Now, the double copy applies in perturbation theory, and people have tried to somehow utilize it to simplify calculations. Double copy like field theory for gravity. So some kind of field theory that tries to take advantage of these simplifications. Actually, one of these entries is a paper of mine with Alex and other people. Gauge invariant approach, so people try to extract classical physics directly from scattering amplitudes, and because the scattering amplitudes satisfy a double copy, then this is useful. People also consider scattering amplitudes, I guess in a kind of different motivation, but still part of the same set of ideas, not just in Minkowski spacetime, but let's say on plane wave backgrounds. So backgrounds where you can still define scattering, you define some asymptotic states and scattering amplitudes. And you had a talk on this by Tim Adamo recently. And a highlight of the use of these double copy methods, and actually also other methods from scattering amplitudes, has been the progress in the understanding the two-body gravitational potential, in particular, mostly its conservative part. So new corrections that order in G Newton cubed and G Newton fourth, which are 3 post-Minkowskian and 4 post-Minkowskian, that contribute then to the analysis of data for the in-spiral phase of a black hole merger. Now, what I will focus most of my talk on is how these ideas actually apply to some exact classical solutions and what are various different ways in which you can do that, which sort of complement each other. So one basic question, and people asked that when I was working on sketching amplitudes in this color kinematics duality, people ask, well, if there's this double copy, then is the black hole a double copy of something? And that is something that looks a bit confusing to think of because, well, what is a graviton? If you have an exact metric solution, it's not obvious what is the graviton part of it. So you have to somehow decompose it into Minkowski plus graviton fields. What sense does that make? It seems to be a complete, generically, completely coordinate dependent way of doing it. You can't just take a metric and subtract Minkowski spacetime and call it a graviton field. Moreover, the rules of the double copy apply order by order in perturbation theory. So so at a given order in gravity in perturbation theory, you import the results of that perturbative order in gauge theory, and then you obtain the gravity answer at that order. So then if you perturbatively expand the gravity solution, each order in that expansion would somehow have its own little double copy. So if you sum over all those orders to obtain an exact solution, let's say a black hole solution, it's not clear what you would be able to see. Still, well, you can relate solutions to perturbation theory as certain solutions, Schwarzschild, shockwave. I mentioned here just a couple of examples, more or less in this context. But you may still wonder if there is a direct map of classical solutions. Well, for that, you would need some sort of miracle, and that miracle can be provided by symmetry, as often happens. The symmetry that I'll be interested in is that of Schwarzschild spacetimes. So this can be thought of as an exact perturbation of some base spacetime, which I will take to be Minkowski spacetime for my purpose. So these spacetimes have choices of coordinates for which you can write the curved metric like this. Phi is just a function, and k is null and geodesic with respect to the flat metric, and therefore you can show with respect also to the curved metric. In fact, you can lower and raise the indices of k with either of them, because k is null. Also, because k is null, the inverse metric just truncates at linearized order also. But much more non-trivially, the Ricci tensor with when in x up, 1 down is also linear in this metric deviation. So basically, Schwarzschild spacetimes, they satisfy properties that you normally only expect in the linearized approximation. But in this case, they are exact. And there are very interesting solutions like Schwarzschild black hole and its rotating extension, the Kerr black hole, which are probably the most important exact solutions we know for astrophysics. They are stationary solutions, so they don't depend on some time coordinates. And this is what I'll consider now, stationary vacuum solutions. You can take the time component of k to be 1. If it's not, I just shove that into phi. And then the time component of the vacuum Einstein equations is just a spatial Laplacian acting on phi, vanishing, and this is the space-time component. Now, if you look at this, so you have here some graviton fields, and this K, well, it's doubled, so you would imagine that the analogous gauge theory solution will have only one of these Ks. So you can talk about a single copy, being somehow the inverse of the double copy, because these linearized the Einstein equations. This linearizes then the Yang-Mills equations, which means that it's an abelian solution. You can just trivialize the color dependence by having some constant color vector, or just get rid of it. So here you have 2Ks, here you have 1K. But this phi is the same. You don't take its square root. And that's because this also happens for sketching amplitudes. You don't square the propagators. That's why there was some inverse propagator factor in some formula I mentioned for sketching amplitudes. Now you plug these into the Yang-Mills equations and they are satisfied. Okay, so
can I ask a question?
Yeah.
So what are the variables of these equations? Yeah, so you have basically 4 equations for phi and for k. K is unknown variable.
So for a particular space-time, as the Schwarzschild example that I'll mention in a moment, then yeah, phi and k have some specific form.
Yeah, and these equations are satisfied. I understand, but if you substitute these ansatz into equations, you should solve it with respect to phi and k, or generically you will not find many solutions.
Well, so there's a class of vacuum Kerr-Schildt spacetimes, in particular also then stationary vacuum Kerr-Schildt spacetimes, and one example of that is the Kerr solution. But let me give you then the example of Schwarzschild, which looks simple. So this is just a very basic example of a spherical symmetric solution sourced by a point mass in gravity or a point charge in gauge theory. So Schwarzschild looks like this in Kerr-Schildt coordinates. The difference with respect to your usual Schwarzschild coordinates is that this t is not the same coordinate. You have to do a little transformation. I put it in an exam once, but somehow it didn't go very well. It's a simple one. The gauge theory solution is actually just a Coulomb solution, well, as you expect just from this description. You can put it in its usual gauge with a little gauge transformation. So the Schwarzschild solution can, in this sense, be thought of as a double copy of the Coulomb solution. And the point is that the main point is to find a way where you decompose the curved solution into a Minkowski part plus a graviton field that is then the double copy of the gauge theory solution. So that's what I mean by this formula. Right, you can extend that to rotating black holes. Now there's another parameter along with the mass. You get the angular momentum. You can go to higher dimensions as an analog of the Kerr black holes called Myers-Perry black holes. There are more planes of rotation in higher dimensions, so you have more angular momentum. There are other black hole families which have no 4-dimensional counterpart, at least ones which have an event horizon, such as black rings, etc. These are not Kerr-Schildt, but they may be closely related, and it will be interesting to know if they also admit a double copy interpretation. You can consider cosmological constants. It's related in gauge theory to a constant charge density, and net charge is related to a magnetic monopole charge. And indeed, long ago, this net charge had been thought of as some sort of gravitational analog of a magnetic monopole charge. But here it's not just an analog. There's an exact map between the solutions. The solutions with this net charge and rotation are multi-Kerr-Schildt type. In 4 dimensions, they are double Kerr-Schildts. So there's this tau net solution where there's a parameter related to the mass and the parameter related to the net charge. And its single copy is then a dion, which has an electric charge and a magnetic monopole charge. So these phi are some functions, but they multiply some parameter, free parameter. You can consider some solutions with radiation, and you can consider many other kinds of situations. which of course I will not go over.
Excuse me.
Okay.
May I make a comment? Maybe there was a question on what conditions for this Schwarzschild vector should be so that it solve the like Einstein equations and Young-Mills equations.
Was this in the chat or something? Because I can't see it somehow. I can't see the chat box. Or you're just asking.
I don't have camera.
Okay, so sorry. Could you repeat your question again?
No, that was a comment. So it seems like for the exact solution, the fundamental feature for Schwarzschild vector is that it's originated from Killing-Gardner tensor, and then it imposes
That's right.
this many.
That's right. Actually, yeah, the story of the Killing-Gardner tensors is very interesting, and in higher dimensions, actually. So here, for this Schwarzschild story, it just works directly. But there's another story that I will mention: the Spinorial approach, another approach which is more based on the curvatures, where I think this Killing-Gardner tensor could actually clarify some aspects. But you will see in a moment. But yeah, that is true, that these spacetimes have a number of symmetries, and that often these hidden symmetries are represented by Killing-Gardner tensors. Right. So that was the basic picture, and now I'm going to tell you some sort of variations of it. So the first is that, well, I told you that double copy of Coulomb is Schwarzschild, but Schwarzschild is just pure vacuum. So what about these Dilaton and B-fields? Well, they can also appear, and I will tell you how. It turns out that actually these fields are all nicely packaged into something called double field theory. And I'm sure you will have seen in the archive these two kind of topics, and perhaps you wonder if this double is related. And there is a relation between them, although it doesn't look trivial, because this double here refers to two copies of gauge theory, and this double represents a doubling of the geometry, but they are indeed related. Right, so, but let's discuss this double copy of the Coulomb solution. And the point is that it's not unique. And to see that, let's just think about linearized plane waves with certain polarization vectors which are orthogonal to the momentum. So if we consider two possible polarization vectors, we can form a polarization tensor. That would be the simplest kind of double copy. But well, that's just a choice. Why not the symmetrized products or the anti-symmetrized products or the dot product times the metric? Or it's not really the metric, it's the space where the polarizations live. So you can fix their gauge by saying that they are orthogonal to some reference vector Q, which is null. And then this is the projector, which is actually the metric on the space, which is orthogonal to K and Q. So in general, this is then the most general choice of double copy for these two particular waves. And I wrote them here in a combination such that this is traceless symmetric. So that corresponds to a graviton kind of polarization tensor. This is the antisymmetric part, a B-field type of polarization tensor, and a dilaton part whose polarization tensor is of this form. So here you see that then you can tune this linear combination as you wish. Right. Now, what would be the counterpart then in Coulomb? Well, first of all, there is no B-field because the B-field comes from the antisymmetric part. And if you're squaring the same solution, so it's one solution times itself, then there is no antisymmetric part to the double copy. There's no B-field. Then this parameter actually in linearized level will be related to the mass. And let me call the dilaton parameter Y. You can actually write the coordinate space analog of this story that is valid for the double copy of the Coulomb solution, and this is actually work with Alex also. I will not go into that here. The exact solution is actually known. So in the same way that when there's no dilaton, we know it's Schwarzschild. When there is dilaton, we know that is the so-called Yanis-Newman-Winnicourt solution, GNW. So let me just tell you just very quickly about it. It's unique static spherical symmetric asymptotically flat solution of Einstein and a minimally coupled scalar, which in this case is the dilaton. As to parameters, M and Y, I can also express it in terms of these rho 0 and gamma. using these relations here. The metric looks a bit like Schwarzschild, except for some funny exponents here. And yeah, so and this is the dilaton. When y is 0, this is just Schwarzschild. And here you can see that rho 0 is 2m, just Schwarzschild radius, and gamma is 1. So this factor actually disappears. But when y is not 0, actually rho 0 is the origin, because when gamma is not 1, then you have this factor here, and so the line elements goes to 0 when rho is rho 0. So this sphere part, this means that this is the origin of your spherical coordinate system, and it turns out that you have a naked singularity there. So yeah, there's no horizon, it's just a naked singularity. Well, this is what you expect from the no-hair theorems. You can't just deform Schwarzschilds with a scalar profile and preserve a horizon. But this should be the general double copy of Coulomb. So this brings home a certain message, which is that, well, in the double copy, you take something from gauge theory and you do its double copy to gravity, and then you have to interpret that physically, okay? So yeah, it's a mathematical map between solutions, and then that solution may have a naked singularity. Right, but is there an exact double copy map then that includes also the dilaton and maybe also the B-field in other cases? Yes, there is, and it uses double field theory. I'll tell you about it briefly. Let me just make the remark that when I do that and I talk about the metric, I will actually talk about the metric in the string frame, which is related to the metric in the standard Einstein frame by a veil transformation that involves the dilaton. Now, for my purposes, double field theory, which is a huge topic, is basically a fancy formulation of this product gravity theory, which is just the massless level of the closed string, this graviton, dilaton, and B-field theory. The motivation for double field theory is to write down this low energy effective theory of the closed string, which is what we are considering, but while still preserving some, so making manifests a property of string theory, which is T-duality. The way that this is done is by doubling the geometry. So you double the dimensionality to twice, such that you have not only the coordinates, typical spatial coordinate that is conjugate to your usual momenta, but also x tilde, a new coordinates in this doubled space that is conjugate to the winding. Because what T-duality does is that it relates string theory, space with some compact, some periodic, some compactified directions, to string theory in a different space, also with compactified directions, but where the radius in one is, let's say, r, and in the other one is alpha prime over r. And when you do that, you then exchange the momenta and the winding. So in general, if you have many compactified directions, there's some linear transformation here between these. And that linear transformation is represented in this doubled space by an ODD matrix. So an ODD matrix satisfies then that its transpose times I times it again is I. And I is just this ODD metric. So if there's some student here, this looks a little bit like Lorentz transformation. It's just a different type of group. So if you write your theory, let's say your equations of motion or your action in a way that is ODD covariant, then T-duality is manifest. It acts linearly with this transformation. Of course, this is actually doubling your degrees of freedom. So you have to then impose a section condition which will break this covariance. So then T-duality is no longer manifest when you do this. And the trivial way of imposing the section condition is to say that your fields do not depend on these winding coordinates. But you may be interested in doing something more complicated than that in the double field theory literature. Right, now for our purposes, what happens is that the metric and the B-fields are, or the string frame metric and the B-fields are nicely packaged into something called the generalized metric, which is a rank 2 tensor with respect to ODD. Moreover, the supergravity field is related to the Dilaton field is related to a so-called DFT Dilaton field, which is also then involves in its relation the metric determinants. And this choice is made such that this is a scalar with respect to ODD, so it doesn't transform. Now, what this allows us to do is to extend these NZs for vacuum gravity to an analogous NZs for this theory that also has Dilaton and B-fields. So you have some bit, which is like the trivial generalized metric, which is just this little metric is Minkowski and there's no B-fields. And then you have a term here that is the analogous to this term. And then you can consider deformations of that. These K and K bar are 2D dimensional. They're based on some little K and K bar, which are null and satisfy some differential constraints, similar to being geodesic. But notice that these two ones differ. There's this minus sign. And then you can read off what this NZs means in terms of the metric. And you can see that this is, it's an extension of these NZs that is motivated by double field theory. And using these, Cancun Lee obtained the first examples of an exact double copy that includes also a Dilaton and a B-fields. And then we considered some extension of that to get a broader NZ that also fits this GMW solution. Now, there's an important insight from this double field theory story, because what happens is that this generalized metric induces a notion of chirality. There are some projectors into chiral and anti-chiral sectors in this doubled space. And these are related in the worldsheet origin of this story to left and right moving sectors on the worldsheets. And that's precisely this KLT origin of the double copy, the relation between the closed strings and factorization between left and right moving sectors, that then each of them looks like an open string. And that's embedded in these NZs because this K and K bar are precisely chosen. Remember, there was some minus sign here, are precisely chosen to have some definite chirality with respect to these projectors. And then the gauge fields that will be associated with each of them will then also have this chirality. So then this gives a KLT picture of the Schwarzschild double copy. So as being something that has precisely the same origin as the story for sketching amplitudes. You can then also look at the equations of motion and find in the equations of motion, I won't go into detail with this, but you can find the Maxwell equations for each of these fields. So the point is that if you have some solution that fits this Schwarzschild-like NZs, then you can decompose it into left-moving gauge field and right-moving gauge fields. And for the case of GNW, these left and right-moving gauge field are just a Coulomb solution.
Excuse me?
Yeah.
Did I get it right that K and K bar are orthogonal to each other?
Well, the K and K bar are orthogonal to each other. Well, not necessarily. Sorry, here this K here was null and geodesic. Now here you have this K and K bar. So what happens here is that as you, in general, then this will not be the case. You have here this K dot K bar. So what happens in the vacuum case is that these two become the same. So B field is 0. And then they are null because each of them is null, but now, because they became the same, then it is null.
So the inverse metric for HMN has some complicated form. It's not like
it's actually not very complicated. No, I know.
I mean, complicated obvious, in the sense it's not a matter of science. It's some factors as well, right?
Yeah, it's basically because of this factor.
Okay, yeah.
It will look a little bit different, but otherwise it will still look pretty close to this one actually, because it's it's true that it's not null, but the structure is still quite special.
Thank you.
Oops.
Sorry, may I ask some, maybe a vague question?
Yeah.
So it looks like you have disentangled K from another K, right? You somehow,
yeah.
Well, in the amplitudes double copy, we always know that we can double copy one theory to another theory, one gauge theory to another gauge theory, and get something sensible. And in gravity, now you also have a way to just map to different kinds of gauge theory solutions and get something sensible on the gravity side, right? Is that what is happening?
Yes. So for instance, you can think about the Coulomb case. So let me.
Well, in the Coulomb case are the same, or maybe you can.
No, actually, K and K bar are not the same because of this minus. So the little k and the little K bar and the little K are the same.
Yeah, I meant the little case.
Yeah, exactly. So yeah, in that case, little k's are the same. But in general, they are not the same. So you can get the B-fields. And indeed, what Kengun found is that many solutions that are known in supergravity that have these three fields actually fit these NZs. I mean, they were found in a different way, but a posteriori, they fit. Because these NZs has been extremely useful in the history of GR. And it's closely connected to the way that the Kerr solution was found. So somehow it's not surprising that many solutions that we know exactly, I mean, if we know solutions exactly, it's because they have some hidden symmetry, because otherwise you can't solve like the Einstein equations. So somehow it was interesting that he found that many solutions that are known exactly actually a posteriori can be checked to satisfy a kind of NZs that is similar to this one.
Mm-hmm. Right. Yeah, but I was just wondering what this K and K bar, they are now different, the small guys, and they kind of belong to different copies, right? To different gauge theory copies. And
yes, that's true.
And you, but I don't quite get this association to right moving and left moving string sectors, because I don't see exactly the connection to string theory here.
Yeah, exactly. It's because the connection here is in this issue of the chirality.
But it's not the space-time chirality, is it?
Well, it's a chirality. You can think about this one as acting on the positions X, let's say, and then you can check what are the combinations that have definite chirality. It's not this X. It's you can define also another X where these two are exchanged. And then basically the object which has definite chirality is ones where this is like X plus X tilde, and then like something like X plus X tilde also here, maybe with a minus sign, and X minus X tilde. So basically correspond to the left moving and right moving on the world sheets. Because basically on the world sheets, the X, remember when you do string theory, you often write X equals XL plus XR. X left and X right. Mm-hmm. And basically this XL and X right are the choices that have a definite chirality.
Yeah, but I meant that it's more like the chirality on the world sheet, not in the space-time.
So what I'm telling you is that the two are related. So in the DFT literature, they are related by these projectors. Mm-hmm. If something has a definite chirality with respect to these projectors, then you can think about it as lying in one of the sectors.
Can I comment on that?
Sure.
Yeah, so the point is that if you consider standard string theory, you have three, say, bosons, and you split them into left and right modes. And you have center of mass coordinate, which is just a constant, which is a zero mode, which defines your space-time. So the oscillators are left and right, and you build your vertex operators out of them. Mm-hmm. But momentum part is still sensitive to center of mass. So px, exponent IPX is what defines the momentum conservation, etc. So now you can do the following thing, which is related to T-duality, where you really have a circle. You can try to double the number of zero modes, or double the space-time constant part. So then X left and X right will become like two independent spaces, now also having zero modes. So that will mean that you have moment and winding modes sort of on par with center of mass coordinates. So that's effectively what is done when you talk about doubling of X's. And that's related to what Ricardo was saying about these operators, etc. So, but that, well, at that level, it's purely kinematical, but indeed, to promote it to world line picture, world surface picture, you need to think of this as zero modes of left and right modes separate, being separate. And that will be X left minus plus X right will be X, and X left minus X right will be X tilde. The one here.
Okay, thanks.
Okay, thank you. Right. Now, perhaps more briefly, I will mention that there's another way of doing this. In fact, when I started talking about it, you might have thought that maybe it's best to start looking at the curvatures rather than the fields, because the curvatures, at least at linearized level, are gauge invariant. So let's say this object, let's say for some plane wave, and if I consider here a plane wave with a factorizable polarization tensor, then this is what you get for R. So you get an obvious relation like this, which you can then try to, extend beyond this trivial case. Well, it's not so simple because keeping the symmetries of these is not simple. And also then beyond linearized level, you'll have to worry about it's not gauge invariance. But still you can proceed. And there's actually a very, very convenient formalism for this. Well, at least in 4 dimensions, but probably also in higher dimensions, which is the Spinorial approach to GR, where here the basic object has a space-time index and 2 Spinorial indices, A and A dots, which have values 1 or 2. And this is basically a Spinorial Vilbine. So yeah, if you know them, you know the metric, and you can also, if you know the metric, construct these objects using the Pauli matrices. Now, what they do is to translate space-time indices into spinor indices. So if you have an index like this, you can turn it into spinorial indices using this rule. And actually in particle physics, this is the starting point of what is called the spinor helicity formalism. And what we want is a formula where we have some curvature, gravitational curvature, being some kind of double copy of the gauge theory curvature with a 1 over scalar. And here the scalar is represented by this, because this is like, if this is the gauge fields, then this is a scalar field. Right, so I'll focus now on the Weyl curvature, which is, well, I'm going to focus on vacuum spacetime. So it's the same as if I consider the Riemann curvature. So we will take to be vacuum. Then the Weyl tensor can be written with spinorial indices and actually has this very simple decomposition based on its symmetries on this Weyl spinor, which is fully symmetric, and then its complex conjugates. So one is like the self-dual one, and the other one is the anti-self-dual one, or the other way around. I guess there are different conventions in the literature. Now you can always decompose this rank 4 spinor into 4 rank 1 spinors. And of course, it's not unique. You can multiply A by a function and divide B by the same function, but it gives you a spinorial direction. And with this direction and its complex conjugate, you can get a space-time direction. So now you could turn this into one space-time index. And there are 4 of them, so you have 4 principal null directions. And these null directions are the basis of an even older classification of space-times that fits very well with the spinorial point of view, but also has another formulation. And the question of this classification is how many of these directions are aligned? So in type 1 is generic, none of them are aligned. In type 2, there are 3 directions, 3 independent directions. One of them has multiplicity 2, So let's say, for instance, that C and D are proportional. Type D that we'll be interested in here, there are two principal null directions of multiplicity 2. Type 3, there are two, one of them multiplicity 3. And type N, there is one of multiplicity 4. And type O is a trivial Weyl tensor, it's 0. But you can see here in type D, I can now define a rank 2 spinor such that this looks a bit like a double copy. So with type D means that the Weyl spinor can be written in this way. Now, let's look at the Maxwell spinor obtained from the field strength. So it's very similar the story for the field strength as it from the one for the Weyl tensor. Just there are fewer indices. This F has now two principal null directions.
Sorry, can I ask a question?
Yeah.
I don't remember. There are, I think, electro-Bach solutions or something like that, where you have a curvature supported by Maxwell field. So you have a gravity coupled.
Right. So here I would actually be considering only vacuum spacetimes.
Only vacuum, okay.
But this should have an extension. But so part of the issue of considering electrovacuum is the following. If you want to turn on the gauge fields in a supergravity-like theory, you need to turn on the dilaton or the gauge field or the B-fields. So let's say the Reissner-Nostrom is not expected then to have a double copy interpretation because it's not the solution of the double copy theory. The solution to the double copy theory, analogous to the Reissner-Nostrom, is the dilaton charged black hole.
Mm-hmm. Okay, thanks.
Okay, good, thank you. So now you can just guess, well, if this type D solution has two principal null directions of multiplicity 2, then they could just be the two principal null directions of some Maxwell spinor. These type D solutions are indeed, they are Coulombic in some sense. They are, well, like they are like Schwarzschild, let's say, and they have no functional freedom. So there are only a handful of parameters, such as rotation, net charge, acceleration, mass, of course. And this, so an example is the Kerr-Taub-Nut solution. Now, this actually matches the previous story that we discussed in 4 dimensions, where this function that appears here, its real part is the scalar that I mentioned before, but also adds new examples that are not stationary. For instance, the so-called symmetric, which represents a pair of black holes uniformly accelerated in opposite directions. And then its single copy is the linear Vischer potential for charges, which are also accelerated in the same way. Now, the geometric origin of this lies in the fact that there's a killing rank 2 spinor underlying this type D solutions. So this was proven by Walker and Penrose that such a spinor exists, and this is the way that the killing spinor equation. So this is like the usual covariant derivative, but now you have to do some change to Spinorial indices. But the point is that there is a spinor such that you can use it to construct the Weyl spinor, where this chi is the norm of the spinor. But then you can also construct a gauge field and a scalar, such that this expression is just comes out of this construction. Now, the point about the double copy is that you can actually think also about this as living in flat space-time. So there are solutions not only on the curved background, which has this Weyl spinor, but also on a flat background. And indeed, you can identify your flat background because these solutions, they admit a double Kerr-Schwild form, actually, if you allow for a complexification of the coordinates. Right. Now, actually, I'm running late, so I'm just going to mention quickly that for type N solutions, there is a similar story where you can relate, well, where you also have this relation for different reasons, not because there exists a killing spinor, but because of the form, the very simple form, where somehow you have an equation for gravity, which is the Bianchi identity for the Weyl tensor, an equation which is the Maxwell equation for the gauge fields, and the scalar equation that implies the scalar wave equation, and they're all of the same structure, and you can use them to show a relation between these that is basically the double copy. And okay, there's a twistorial interpretation to these things that was recently pointed out, and it will be interesting to then apply it to the cases of type N and well, to see what is the range of this. And now finally, I'll just make very brief, sorry?
Excuse me, do you have in this previous case for, what you call it, for degenerate Maxwell field, do you have a functional freedom for S, or there is no functional freedom in that?
Yes, exactly. So these solutions, as opposed to type D, which are fully determined up to a few parameters, these are a functional freedom, and that enters because you also have some freedom then of choosing this S.
Yes,
so the relation is like relaxed in a way. In the other case, they're basically, the functional dependence is fully determined. Yeah, thanks. Okay, so now just very briefly at the end, a more direct relation to scattering amplitudes. Well, let's think about how you would, let's say that this is a charged particle and it emits a photon. And you can think about measuring the fields generated by the charged particle, but with a diagram like this. We'll consider this diagram to be fully on shell. So this is on the mass shell and also the photon. Then you can calculate the 3-point amplitudes. And these are the building blocks of modern on-shell methods. For instance, the BCFW recursion, where you calculate, let's say a 4-point amplitude in terms of 3-point amplitudes instead of using Feynman diagrams, and a 5-point amplitude in terms of 4-point amplitudes and 3-point amplitudes, and so on. But there's an issue, which is that this amplitude doesn't exist if you have Lorentzian spacetime with real kinematics. Then, I mean, you can go to a frame where this is stationary as energy m, and this is static and as energy m, so you can't produce a photon out of it. But you can support it on complex kinematics. And indeed, this BCFW recursion is based on complexifying the kinematics and using some complex, like the residue theorem. But you can also consider a split signature, so having 2 times, and then it can be supported in real kinematics. And sometimes, depending on your somehow application, this may be more convenient. Right, and what we will be interested in next is actually taking the classical limit of the amplitude. And the way that works is that, there's already something here quantum, because if you have a massless particle, the momentum is h bar times the wave vector. And the classical limit is taking h bar to 0 while keeping the wave vector finite. And there's a new formalism, the Kosover, maybe O'Connell formalism, that gives a prescription for calculating certain observables, you systematizing these limits by using only scattering amplitudes. And if you do that, then you conclude that these 3-point amplitudes compute the linearized curvature and for the gravity case and the field strength in the electromagnetic case. And we chose them to be in some split signature so that the kinematics is real and these integrals are easier to do. So the point of the formalism is that you take some operator, let's say the field strength, you can expand it in creation and annihilation operators, and then its expectation value will be given with respect to some state, which we interpret as an out state given by an S matrix times the in state. This S matrix is the identity plus some amplitude. And this in state, in our problem of interest, in the in state, there is only this particle. And in the out state, we have the particle and the photon. Well, maybe I should have pointed this upward, but okay, I think you get the picture. And what you get then after a calculation is that, in the classical limit of this object, you have a quantity that is a real part of some inverse Fourier transform that is supported here on null momenta. And here is a future pointed, and this is then something that is related to the 3-point amplitudes. And these are the examples that we'll consider. Now, let me just mention that since it's supported in null momenta, you can consider like a spinorial version of this K, where the two spinors are factorized like this. So you can do this when the momentum is null. And this kind of notation for the two spinors is a common notation in particle physics in this so-called spinor helicity formalism. But this is the n-dotted spinor, and this is the dotted spinor, the chiral and anti-chiral, if you want. Now, if you do this and calculate here the Weyl spinor in coordinate space, then this object here will be this one. And so you can, the indices come in these chiral spinors, and here you have also an amplitude, which is chiral in the sense that this is the amplitude for a massive particle to emit a positive helicity graviton. If we wanted the other chirality, so this would be its complex conjugate, here we would use these kind of spinors here, and this would be a negative helicity graviton. And then you have the analogous thing for gauge theory, charged particle, photon. This is the amplitude for emitting a photon. Well, I guess there's a constant in front, which is the charge of the particle. This is the momentum of the particle, and this is the polarization vector of the photon. And you can also consider a scalar example where this is just a constant. You can consider that the amplitude for emitting it is a constant. And if you plug it in here, you basically get 1/r, but in split signature. So you have to analytically continue. Choose one coordinate, let's say z, and continue it to the second time. So it's very simple continuation. This one you get Coulomb, and this one you get linearized Schwarzschild. Now you can see that this already looks a little bit like a double copy, and it will look completely like a double copy when you realize that this amplitude to emit a positive helicity graviton is the double copy of that to emit a positive helicity photon. And then you have a relation of this type, which is this sort of Weyl double copy, but now in this on-shell momentum space. If you go to coordinate space, yeah, you can identify the solutions as I mentioned previously. But it's quite surprising that you have something that is like, you have some product in momentum space. What you expect is to have convolutions in coordinate space. And generically, this is what you should expect. And there is a linearized double copy map based on this idea of the convolution. Here, this is an on-shell version of that in momentum space. So the cases that I presented before, the symmetry of these solutions is making something that is actually originally a double copy in momentum space look like something that is very simple in coordinate space. But that's not the general story that we expect. All right, so apologize for going some minutes over time. This double copy story has proven very useful in various fields, from string theory to supergravity to now gravitational waves. A double copy of exact classical solutions is possible. The main point was to identify how to decompose the solution into a trivial bit and a graviton field. That is actually the double copy of the gauge theory solution. There are various approaches that are complementary and consistent, and they exploit the algebraic structure of the solutions. They also exploit somehow the stringy insights, such as in the case of double field theory. And yeah, you can check in various cases that this is the same kind of double copy as the one for sketching amplitudes that appeared originally. And well, there is much more to explore: largest classes of solutions, duality transformations, asymptotic symmetries. Yeah, what is the double copy for generic solutions of the equations of motion? So that is an important question. And finally, things that I did not discuss at all: the color kinematics duality in gauge theory is still a topic of research. In fact, there was a paper today of more than 150 pages on it. So that's very important in implementing this duality for sketching amplitudes. There's also the topic of relation between field theory amplitudes and string theory amplitudes that is really illuminated from these notions of the double copy. And there is much more to be said about that. And I think I will conclude here. And yeah, let me know if you have any questions.
Thank you. Are there any questions?
I have a question, the kind of more philosophical one. So if you think of scattering amplitudes, on-shell amplitudes, so the generating function for tree-level amplitudes is basically classical action evaluated on general classical solution with some initial data, right? So if you know all scattering amplitudes, in principle, you can imagine you can reconstruct general solution. Now, sort of like
so the issue is the off-shell lag that you need.
Yes, yeah, but let me finish with where I'm going. So, so in principle, you have, say, double copy for in string theory, which is simple only for 3-point or 4-point amplitudes, right? So if you go to higher point amplitude, it will be very hard to tell what's the relation.
Actually, in sort of more recent progress on that has actually obtained an n-point formula for it. Now, and it formula also as a smooth field theory limit also. It's based on something called the momentum kernel.
Okay.
So there's like an optimal way of doing it, which was not explored in the 80s.
Still to finish, yeah. So I guess where I'm going to, so it looks like the examples where you do have simple double copy are very special in the sense they have hidden symmetry. Well, they have symmetry, which makes this relation much simpler than you would expect in general. So that's somewhat reminding integrability, or where high point amplitudes are actually determined by 4-point by factorization, something like that. So it could be that this double copy works in a simple way only in examples, which needs to be classified. Is that how it should be? Because I can't imagine, say, constructing generic solution in similar way in some systematic fashion. It probably will be a complete mess if I try to rewrite relatively complicated gravity solution in terms of some kind of gauge theory solution.
Yes. So, it's a bit hard to answer the question. It's one of those things that, if someone told you 20 years ago, maybe that you would write the KLT expression in a nice closed down formula, then maybe that would also sound a bit surprising, because it does look very messy. Now, it's true that these solutions, like an important factor of this solution that I mentioned, is that although the double copy relates Yang-Mills theory to gravity, the solutions that I mentioned, classical solutions, were all Maxwell solutions. And that's basically related to your question, because this means that the solutions in gravity that I discussed are in some sense, in some hidden sense, linear solutions. For instance, the Kerr solution, because they are Schwarzschild, they can be written in a way, but it's something that is not obvious a priori. And that's why their single copy is just a Maxwell solution and not a solution where you need non-trivial Yang-Mills. On the other hand, what you can do, and what people have done in the context then of these double copy-like field theories that I mentioned, that were motivated by looking at gravitational waves, is to just look at perturbative solutions. And then you do it in Fourier space. And there, then I guess depends on your problem, whether that is the most effective way of doing it or not, but it's not, let's say, I agree that a coordinate space nonlinear map is something that is quite, that should look quite non-trivial. Beyond this simple class of solutions. On the other hand, we also know that some features are actually best looked not in space-time, but let's say, for instance, in twistor space, or in something called ambi-twistor space. There are geometric aspects, especially these ones that look non-local, which can be more appropriately expressed in different kinds of spaces. So there's a connection of these to the so-called ambi-twistor strings, which I didn't mention, but where, well, it suggests that space-time is not necessarily the way to write a generic map between classical solutions, but that instead other representations of the classical solutions may help with that. And I wonder actually if this recent work by Chris White on a twistorial representation of this vial, of this Spinorial double copy, if it may somehow move more in that direction. But I also ask you, well, in Yang-Mills theory, so the problem is that we don't have many examples of exact solutions that we know in Yang-Mills theory, which are continuously connected to the trivial solution, right? And the ones that we do somehow, and even the ones that don't seem to be, they are sometimes related, let's say, by a singular gauge transformation to ones that do. My approach has been, let's find a solution that we understand and try to understand that solution. And then it always turned out that that solution was somehow quite simple, but it is just because if we can write down the solution, it's because it's very simple. And there's probably a way of writing it. It's a solution of some integral system, some integral subsector of the Einstein equations. And in some sense, that solution is linear in some approach.
Okay, well, thank you. Yeah, indeed, I think what is also important is that indeed both gauge theories and string theory comes out of gauge theory and gravity come out of string theory, in which there is a very basic type of interaction, which is kind of splitting and joining strings. It's cubic effectively. Mm-hmm. That's also the basic interaction which controls both gravity and Yang-Mills. So if one could think of some other kind of field theories, certainly nothing like that would work there. So it's very specific to these two theories somehow.
Well, actually, there is a wider range of theories which have, in the same way that gravity is a double copy of gauge theory, there is a special Galilean theory which is a double copy of the nonlinear sigma model. So I focus this more on gravity and gauge theory, and that's where I think, well, much of the focus has been time that the same kind of map between sketching amplitudes actually applies to some other theories which have also a sort of cubic type interaction. Well, of course, their Lagrangian looks like it has an infinite number of vertices, but actually, if you think about it in an appropriate way, you can find a representation that obeys, for instance, this color kinematics duality, and then you can do the double copy and you can identify the other theory. So there is a web of theories that are related by these kinds of rules. And even, of course, in the just gauge theory and gravity case, you can have different kinds of gauge theory with different degrees of supergravity, different multiplets, and people have tried to somehow probe the space of supergravity theories that you can obtain with this for various sort of practical applications. So what those theories do have is a kind of string theory formulation, but maybe not quite string theory, but there are these ambitwistor strings which are a bit more permissive. I mean, they are also not necessarily well defined as string theory must be, by which I mean, you can calculate loop integrands. It doesn't mean that they are UV then well behaved, but you can calculate rules that allow you to do something that you could also do, let's say, with a Lagrangian in many cases. And these models exhibit also this kind of double copy structure, similarly to string theory.
So I would like to add and maybe ask. I also agree that at the level of classical solutions, the double copy solutions that we know so far, they all seem to connect to electrodynamics, right? To the abelian case. We don't know any classical cases where we can really exhibit something non-linear.
Well, I guess it depends what you call nonlinear. Would you call a black
well,
hole?
I'm just saying that I'm basically trying to recall that indeed at the level of amplitudes we have the duality that needs to be satisfied for the double copy to work, to go from gauge theory amplitudes to gravity amplitudes, at least at loop level, or in the context that's slightly different from the KLT. And this is something that I have really not seen in classical solutions. That's like a whole enriched theoretical structure that should somehow be there as well in the classical sense, but we just have no idea how to access it, right?
Yeah, so I think to do that, you can then probably construct perturbative solutions. But of course,
yeah, that's what we were trying to do.
So somehow, I think that if you try to do Schwarzschilds in a bad gauge, then you'll need to do that.
Yes.
But then, yeah, well, it might be worth doing it just to see how instructive it is. Because if you do it in a bad gauge, then it won't look linear, and you will look, you will have, you won't just have, the leading order contribution.
Yeah, but we were doing that, the two of us and collaborators. We were doing exactly that, right? We were constructing a perturbative, in a perturbative way, we were constructing the GNW. And yeah, we were struggling beyond 3 points, because beyond 3 points, perturbatively, we were supposed to impose the duality somehow. And to make things work, we had to massage our vertices and so on.
Well, I think the difficult thing, the challenge there was that we wanted to compare them to a solution that was known in a different gauge and field by definition. And I think that is the issue. You can, let's say, obtain a solution using a certain fields, but then you can do one of two things. You can either compute a gauge invariant quantity, which is dependent on field by definitions or anything like that, or you can try to then compare it to some known form of the solution. But then, of course, the transformations between the two forms of the solution are complicated. And I think that was the main complication.
Yeah, absolutely. The complication was that indeed we were looking at the metric, maybe with the field strengths and curvatures, it can be done better. And maybe at that level we can access something really nonlinear and really revealing some classical counterpart of the duality on the gauge theory side. Yeah, it's more like a comment. I also wanted to see if you somehow knew about something I didn't know about.
Well, I think in this context, so there are solutions such as a monopole solution that can be obtained from an abelian solution via a singular gauge transformation. This was something that actually was explored by Chris and a couple of students recently. So that is an example somehow that is on abelian, but then the procedure is still to take it to the abelian case, and then you add a double copy, but it's a double copy that you expect. Yeah, because it gives you the Taubnet solution, which is somehow the gravitational monopole.
Yeah.
Well, I guess the thing is that either you do something in perturbation theory, but then what is the problem that you are trying to solve, right? And or you do something to match an exact solution that is known, but that exact solution that is known has hidden symmetry for sure, and probably can be written in some fancy way that will make this very simple, as these solutions that I've been mentioning.
Yeah. Well, I would just maybe think about some Young-Mills solution that has a non-trivial gauge gauge theoretic structure, right? The group structure that's non-trivial, and then see if that could be mapped to something sensible on the gravity side. Like the Toft monopole thing. Is it monopole? Is it?
So I think what you looked at was the Wu-Yang monopole.
Right. Oh.
But then well,
is it in Yang-Mills?
Actually, how many gauge theory solutions do you know where you have a parameter that you take to 0 and you get a trivial solution? Because this is also the issue. Many solutions have some topological numbers, and then you can't just continuously connect them to Minkowski spacetime. So then, if that solution can be then understood in this story, there has to be an extension of how we understand it. Of course, there are also solutions with topological numbers in gravity.
Yeah. But we don't know about any.
But if you try to look at it, you can't also use this perturbative point of view, because those solutions do not have, they can't be understood perturbatively around.
Yeah. You have to really find the non-perturbative equivalent to that. But we don't know anything about anything like that, do we? I don't remember anyone doing seeing anything like that.
So yeah, a possible story here, application also of this is that when you try to then do perturbation theory on these backgrounds, if the backgrounds are related by the double copy, then there should be a double copy of the perturbation theory on those backgrounds. So let's say gravity perturbation theory in a background is a double copy of gauge theory perturbation theory on a gauge theory background. And so in the backgrounds being related by the double copy will help you see that the perturbation theories are related by the double copy. And the recent work actually by Tim Adamo and collaborators on scattering in non-trivial backgrounds is somehow in that direction.
Mm-hmm.
A question. Do you have any example of double copy interpretation of the solution which is not of D-type or this degenerate type?
D-type or N-type? Well, actually, in this very recent paper on this twistorial formulation, there was also a type 3 type, which is
like the D-type black hole solution is it's 5-dimensional, but that fits, right?
Excuse me, it's 5-dimensional. Sorry, could you repeat?
I mean, I know 3 type is okay. No, it was.
No, yeah, 3 type. It's some algebraic type related to the number of. But the point here is this: any generic solution will be of type 1. We'll have 4 distinct principal null directions.
Yeah,
every one of these. I mean, this is just like Weyl flat, let's say. Any solution of this is so-called algebraically special.
So you're saying on type 3 that there is some solution which admits.
Yeah. So there was an example which I think will be fleshed out more in the near future of something like this, basically using somehow a bit like one gauge theory solution which has 2 principal null directions and another gauge theory solution which is degenerate, which has 1 principal null direction of multiplicity 2, and then if you match one of the 2 with the one from the degenerates, then you get 2 principal null directions, one of them of multiplicity 3.
Mm-hmm.
And then the question is how you do that while guaranteeing that you're solving the equations of motion.
Mm-hmm.
And yeah, it will be so. Yeah. So there is an initial example along that direction.
Sorry, is that an example where some D-type solution, the sum of D-type solution and the N-type solution is again a solution, a linear solution, or it's
well, if it's a linearized solution, then they are solutions independently somehow. They individually, well, I guess you could consider that somehow they are solutions because one somehow compensates the other, but probably because they have different algebraic types, that won't be the case. Yeah, I mean, you can superpose.
In general, sum of two wild tensor is not a solution of nonlinear equations, right? But in that case, it might be some specific example when it still works. That was the question.
So yeah, these examples that I gave here are nonlinear. However, they are algebraically special. Now, if you then try to make them linear and superpose them, and then try to make them nonlinear, yeah, that would be a way of somehow going, going beyond the linearized theory in a non-trivial way. Because then, of course, at next order in perturbation theory, they will like interact.
Yeah.
So yeah, but you can in principle correct the solution order by order in perturbation theory, and you will obtain something which probably is going to be, well, depends how you choose the algebraic some structure, but probably is going to be a generic type.
Okay.
Sorry, but again, in Chris's solution is also connected to an abelian gauge theory solution, right? Just to remind me.
What paper are you talking about?
Well, Chris's white 20 that you referred to get into type. Sorry?
The twistorial.
Yeah.
So I was talking about another paper, a different one.
Oh, but okay, maybe I phased out.
Yeah. So yeah, I was talking first about some monopole, and then about this twistorial story that is more recent.
Okay, good. I don't see any other questions. So thank you very much for a nice talk, and to everyone for participating. And see you next time.
Well, thank you for the invitation.
Thank you.
Bye.